Assalamualaikum and hi everyone. In 2.3 electronic configuration of atom, we will discuss on the Aufbau Principle, Hund's rule and Pauli exclusion principle in filling the electron in orbitals. And we will write the electronic configuration of atom or monoatomic ions by using SPDF notation and orbital diagram. Please stay with me until the end of the lesson and enjoy your learning. In 2.2 quantum mechanics, you have learned quantum mechanical model to define what is orbital. So orbital is three-dimensional region in space where there is high probability to find the electron in an atom. So perhaps by now you have already understood on how we could find the electron in an atom according to this quantum mechanics. In 2.3, you are going to learn electronic configuration. So in this subtopic, you are going to learn on how to fill the electron into the orbital. So this orbital, we have found the different types of the orbital in 2.2 quantum mechanics. So by applying the orbital that we have found in each energy level in quantum mechanics, we will use the same orbital here in 2.3. So but now in 2.3 we will have our proton number and we are going to insert or fill the proton number into the orbitals. Please remember, proton number equals to number of electron. Jadi, di dalam 2.2 you dah belajar tentang tempat-tempat ataupun lokasi di dalam atom yang mana kebarangkalian untuk kita jumpa elektron. Okay, so dalam 2.3 pula, okay, daripada tempat yang awak dah jumpa dekat sini, dekat 2.2 ini, kita akan guna pakai di dalam 2.3 untuk kita mengisi elektron di dalam orbital tersebut. So that's why you learn the place, okay, to fill the electron first. Later, barulah kita akan isi elektron di dalam orbital tersebut. The way electrons in the orbitals are arranged around the nucleus of the atom is called the electron configuration. So this electron configuration describes the distribution of electrons in orbital in an atom. Okay, electron configuration ini menerangkan tentang cara susunan elektron di dalam orbital dalam sesuatu atom. And there are two methods to write electronic configuration. We have orbital diagram and SPDF notation. In order to write electron configuration, we can use orbital diagram or SPDF notation. Here are a few examples of orbital diagrams. We have box, platform and concentric circle. But the most easiest one will be the platform. Kenapa? Because mudah dan cepat. Okay, as you can see in this platform orbital diagram, so we have this platform as our orbital, and the labeling of the orbital must be labeled at the bottom of the platform. So from here, how do we know 1s has one orbital, 2s has one orbital, and 2p has 3 orbitals? Now, let's recall what you have learned in 2.2. So, in 1s, we have n equals to 1 and L will be 0. So, when n equals to 1, L equals to 0, meaning that we will have 1s orbital. But when we have n equals to 2, the value of L could be 0 and 1. So hence, we will have 2s and 2p. So to know how many subshell in 2s and 2p, so later you have to look at the value of ml. So when the value of L is 0, the value of ml also will be 0. So when ml value is 0, so now we have one number over here. So that means in 2s orbital, we will have one orbital only. And for L equals to 1, for N2 L equals to 1, which is 2p orbital, the value of the ml will be from negative L, which is -1 until +1. So how many numbers do we have for ML? We have -1, 0, and +1. So how many numbers over here? 1, 2, and 3. So we have 3 values over here, or 3 numbers over here, showing that the 2p will have 3 orbitals. So that is the reason why we have 1 orbital for s orbital and 3 suborbital for p orbitals. And you must also remember on how many electrons that we should fill this 1 orbital. According to the MS, this 1 orbital can be filled maximum of 2 electrons. The second method is SPDF notation. So in SPDF notation, we will write in terms of this sequence. So from here, if we have 1s2, in SPDF notation, we will write as 1s2. So 2 is the number of electrons that lie on this 1s. And for 2s, since we have 2 electrons over here, so the labeling here will become 2s2. And this 2 also is the total number of electrons in this 2s. And for 2p, since we have 4 electrons over here, it will be written as 2p4 over here. Okay, so 4 ini merujuk kepada number of electron in this 2p. So this is the SPDF notation. Okay, the superscript here belongs to the number of electrons for each orbital. In order to arrange electron in a proper electronic configuration, we have to consider these rules. So these are the rules in electronic configuration that we have to obey before we start filling the electron into each orbital. They are Aufbau Principle, Hund's rule, and Pauli exclusion principle. The first rule is Aufbau Principle. According to Aufbau Principle, electrons will fill orbitals in the increasing order of orbital energy level. Electrons fill with the lowest energy orbital first and the other orbitals in the order of ascending energy. So in this order of increasing energy level, we can see that 1s is the lowest orbital with the lowest energy level, followed by 2s, 2p, 3s, and 3p. So according to Aufbau Principle, kita kena isi elektron pada orbital yang mempunyai tenaga yang paling rendah dahulu, okay, followed by the other orbitals later on. And according to Aufbau Principle also, you have to fill electrons in this 1s orbital completely before we move to the other orbitals after that. So for example, we have 5 number of electrons. So in order to fill these 5 electrons in our electron configuration, the first electron must be here. The second electron cannot be here. Why? Because we haven't filled the 1s orbital completely. Please remember, in one orbital, you have to fill with maximum of 2 electrons, okay? Because 1s is the lowest energy level orbital. So it must be 2 electrons in 1s, and then the rest will fill in 2s completely. And for the balance, then baru kita akan isi pada 2p orbital. So this is the sequence of the energy levels in order to fill the electron. According to Aufbau Principle, electron must be filled in the following order of orbitals. So generally, we must fill electron according to the number of the energy levels. So first, you have to fill electron completely in the first energy level. Then you have to move to the second energy level, third energy level, fourth energy level, and so on. So this is the increasing order of energy levels according to Aufbau Principle. We have 1s as the lowest energy level orbital, followed by 2s, 2p, 3s, 3p, 4s, 3d, 4p, and 5s. So from this arrangement on the left, we can see that since 1s is located at first energy level, so its energy will be lower than the one that located at second energy level. But here we do have some irregularity between 4s and 3d. So for this empty orbital, kita belum lagi isi dengan elektron. So for this empty orbital, the energy level of 4s here is a bit lower than the 3d. Okay, so why is it so? We can answer this question by looking at this arrangement. And also, do you have to memorize this arrangement? Is it difficult to memorize this arrangement? So to answer that question, let's see this image. So here we have different types of orbital. So for the first energy level, we have 1s orbital. For second energy level, we have 2s and 2p orbital. For third energy level, we have 3s, 3p, 3d orbital. And for fourth energy level, we have 4s, 4p, 4d, and 4f energy level. So firstly, you need to arrange these orbitals according to their respective energy levels like this. How we can get these different energy levels? The answer is you have learned this concept before in 2.2 by relating the value of N, L, and ML. So by considering these three values, you will get the orbitals for these respective energy levels like this. Okay, so now we are going to move our cursor to these orbitals. Let's start with the 1s. So we will travel in 1s. We have touched 1s, and then later we will touch the 2s, and then we will touch the 2p, then 3s. Later we will touch the 3p and 4s, and next 3d, 4p, 5s, and etc. So as I move my lines crossing, okay, since I move my lines crossing this orbital, so this will give you the idea on how to arrange these orbitals in the sequence of the increasing energy level. So we start crossing the 1s just now, and then 2s, later 2p, 3s, 3p, 4s, 3d, 4p, and 5s. So by doing this activity, okay, by doing this trick, okay, you will be able to get this arrangement of orbital according to Aufbau Principle. Okay, and please remember, between 4s and 3d, for the empty orbitals, the 4s energy level is slightly smaller than 3d. In this image, you can see clearly the positions of the orbitals according to their energy level. So we have the 1s orbital at the bottom of the energy level here, showing that it has the lowest energy, and followed by 2s, 2p, 3s, 3p, 4s, and 3d. So 4s position is a bit lower than the 3d. So this position is actually for empty orbitals. Okay, so sebelum kita isi dengan elektron, kedudukan 4s memang sedikit rendah daripada 3d. Okay, so ini yang menyebabkan you have to fill the electron in 4s first, then barulah pada 3d. And then we have the 4p, 4d, and etc. So according to the sequence of arrangement, in order to fill the electron, you have to fill fully in the 1s, and then move to 2s, 2p, 3s, 3p, 4s dahulu, and then barulah pergi kepada 3d, 3p, and etc. Second rule is Pauli exclusion principle. So according to this principle, no two electrons in an atom can have the same sets of quantum number. So what is set of quantum number? Set of quantum number will has all this value: N, L, ML, and MS. So one electron will has one set of quantum number. different electrons will have different sets of quantum number. So we can see that this set quantum number is going to be used to characterize that single electron. So in this case, there will be no two electrons. Tiada elektron yang sama yang akan mempunyai set quantum number yang sama. Sebab this quantum numbers is the characteristic of one electron. Only two electrons may occupy the same orbital or subshell, but the fourth quantum number ms is different for both electrons in the same shell or subshell. Electrons must have opposite spins, and the arrow upwards will show clockwise spin and arrow downwards will show anti-clockwise spin. So what does it mean by all these statements adalah, for example, let's say we have 2s orbital. So in this 2s orbital, you are going to feel two electrons in that orbital. So in order to fill these electrons, you have to make sure at this point only two electrons may occupy the same orbital or subshell. So we can feel as much as two electrons in this orbital. And then according to ms, fourth quantum number, spin quantum number, the value of ms is different for both electrons in the same shell or subshell. Okay, how are they different? In terms of the opposite spin. So in order to arrange these two electrons in this orbital, you must arrange according to opposite spin, meaning that satu anak panah ke atas, satu anak panah ke bawah, supaya the value of the ms will be different for both electrons. Bila anak panah ke atas, this is clockwise. So probably the value of the ms will be plus half. And for the anti-clockwise, the value of the ms will be negative half. So that is the meaning of the different value of ms in this orbital. So according to these two values, we can see that in one orbital, we can fill with maximum of two electrons. If we study the quantum number, the set of quantum number for this electron here, we will get the first electron here, the value of n is 2. The L value is 0 because it is s orbital. The ML value will be 0 due to the value of L0, and the value of ms will be plus half. So the set of quantum number for that electron will be 2, 0, 0, and plus half. And for the second electron here, its set of quantum number will be 2, 0, 0, negative half. So that is the meaning of the first statement here. No two electrons in an atom can have the same sets of quantum numbers. Even though we have two electrons in the same orbital, tetapi each of these electrons will has different set of quantum number. So that's why this set quantum number can be used to characterize an electron. Okay, digunakan untuk nak characterizekan satu electron. Can we accept this electronic configuration? Can you check their set of quantum numbers? And since the arrow is also upward, so the value will be plus half. So here, we have two electrons in the same orbital, but both of them are having same set of quantum number. So according to the first statement here, no two electrons can have the same set of quantum number. So this kind of arrangement is forbidden or incorrect. The third rule will be Hund's rule. According to Hund's rule, for degenerate orbitals such as in p and d orbital, the most stable arrangement of electrons in orbitals of a subshell is the one with the greatest number of parallel spin. So electron will occupy singly with parallel spin, and the remaining electron will continue with opposite spin. So for example, we have a number of electrons 7. So to fill the 7 electrons, firstly you have to completely fill the electron in 1s, because 1s is the lowest energy orbital. And then the remaining electron we will fill in 2s orbital. And from here we have another 3 electron balance. So the 3 electrons must follow this Hund's rule, yaitu you have to occupy the electron singly with parallel spin. Bermaksud you have to fill with single electron in parallel spin dahulu. So this will be the correct arrangement according to Hund's rule. Can you write the remaining electron in this sequence? So since we have another 3 electron remaining, can we arrange according to this sequence? The answer is cannot, because this does not follow Hund's rule. Okay, so we will accept the first arrangement, okay, at the above here. And then let's say we have number of electrons 9. Let's say we have 9 electrons. So now we have 2 electrons on 1s. You have filled as much as 4 electrons, so we have another 5 electrons remaining. So these 5 electrons, what you have to do first, you have to fill or occupy the orbital secara singly with parallel spin. So the other 5 balance electron ini, so how to susun dia adalah start dengan single electron in parallel spin, and the remaining electron you can continue with opposite spin. Okay, so here we have successfully filled as much as 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. In order to write electron configuration of neutral atom, we must identify the number of electrons from its proton number. We can get the number of electrons directly from the proton number. So in this example, we are going to draw the orbital diagram and SPDF notation for potassium 19 and chlorine 17. So first, we are going to draw the orbital diagram for potassium 19. So what you have to do first is you have to draw the empty orbitals according to Aufbau Principle. Do you still remember the sequence of empty orbitals according to their energy levels? As you can see, I did draw a huge gap between these orbitals, showing that they are having different in their energy values. And for the 2p orbitals and 3p orbitals here, these 3 orbitals are quite close to each other, showing that they are degenerate orbitals. Okay, orbitals that having the same amount of energy. So in order to fill electron in these orbitals, you have to consider the 3 rules that you have learned in the previous slides. So firstly, you have to consider the Aufbau Principle. You have to start filling the electron with the orbital that having the lowest energy level, and keep filling until you reach these degenerate orbitals. For these degenerate orbitals, you have to apply the Hund's rule, where the electrons must be filled singly in the same direction first. Then we will pair up the single electrons. 18, 19. So now we have put as much as 19 electrons into this orbital diagram. So please bear in mind, in drawing this orbital diagram, you have to label the orbital at the bottom of the orbital diagram, and the amount of electron must be labeled on top of these orbitals. Next, in order to write the SPDF notation, we can refer to the sequence in the orbital diagram. So in 1s, we do have 2 electrons, so we can write as 1s2. So this will be the answer for orbital diagram and SPDF notation for potassium 19. Let's try doing for chlorine 17. In empty orbital, the 4s orbital is more stable than the 3d orbital. So here you can see that the energy level of 4s is a bit lower than the 3d. So in the case of the electronic configuration of transition metal atom, you are required to fill the electron in the 4s first, then the 3d. As the electrons occupy the 3d orbital, the 4s electrons are repelled to a higher energy level. So after we occupied all this orbital with electrons, now the energy level of 4s will go a bit higher than the 3d. So what you have to do next is you have to move the positions of this 4s at the back of the 3d. So untuk orbital yang kosong, kedudukan 4s orbital berada di hadapan 3D kerana energy level of this 4s is a bit lower than the 3D. But once kita dah isi dengan semua elektron dalam this orbital, energy level of 4s will go a bit higher. So what you have to do next is you have to ubah kedudukan 4s dan tulis di belakang of 4s. Okay, so this kind of electron configuration usually akan berlaku dalam transition metal atom. For electronic configurations of the ions, you must be able to identify the number of electrons from proton number. In the case of the cation will be formed when the neutral atom loses electron. And what is the purpose of forming the cation? So the purpose of losing electron to form cation so that the ion formed later on can achieve the stability as in octet configuration or octet stability. In this example, we are going to write the electron configuration for Na+. So before we write the electron configuration of this cation, you have to write the electronic configuration of the neutral atom. So in this neutral atom, the outer shell here is so-called valence shell. And the electron on this valence shell is called the valence electron. And all these orbitals are called inner shell. In order to form cation, that is removing the electron, the process will occur at the valence shell. So in this case, in order to form Na+ ion, we need to remove one electron from sodium atom. So now this will be our new ionic electron configuration for sodium plus. So in this new ion configuration, we will have this orbital as valence shell. So in this valence shell, we do have as much as 8 electrons. So that means this ionic configuration of sodium plus has achieved the stability of octet. In order to write the electron configuration of aluminium 3+ ion, we will start doing with the same step like previous, iaitu writing the electron configuration of the neutral atom. In order to form aluminium 3+ ion, 3 electrons must be removed from the valence shell of neutral aluminium atom. Aturan untuk kita remove elektron adalah kita buang satu elektron dahulu daripada 3p orbital, then next we will remove 2 electrons from the 3s orbitals. So here will be the new electronic configuration for the aluminium 3+ ion. So in this new ionic configuration, we do have 2s and 2p orbital at the outermost energy level. So this 2s and 2p orbital now will become the new valence shell for this ion. In this valence shell, we do have as much as 8 electrons. So we can see that by having this ionic electron configuration, the configuration for the Al3+ has achieved the stability of octet. So that is the purpose of forming the cation. An ion will be formed when the neutral atom accepts electron. So in this case, we will see that the number of electron will be more than the number of proton. So in order to write the ionic configuration for this anion, so macam biasa, as usual, you have to write the electronic configuration of the neutral atom. Now, in order to form oxygen 2-, so 2- meaning that this neutral atom has to accept 2 electrons. Oxygen has to accept extra 2 electrons. So again, in order to accept electrons into the orbital of oxygen, this process will occur at the valence shell. So where is the valence shell of the oxygen? So now we can write the new electron configuration of this ion O2-. The extra 2 electrons here will be added at the valence shell or outermost shell. In this new ionic configuration, we do have as much as 8 electrons in this new valence shell. So this anion has already achieved the stability of octet configuration. So that is the purpose of forming the anion and cation. Now, let us try this example. You may pause this video for a while and try to do the electronic configuration by your own. Later, you can check the answer with my scheme. This is the electronic configuration of the ferrum-26. According to the Aufbau Principle, since the energy level of the empty 4s orbital is a bit lower than the 3d, so hence we will fill electron into the 4s orbital than the 3d. After you have got this configuration, please make sure you move the positions of the 4s orbital at the back of the 3d to become like this. In order to form electronic configuration of the transition metal ions, we have to remove the electron from the orbital that having highest energy level and farthest from the nucleus. So as you can see from this electronic configuration, this electron is located at N4, this electrons at N3, this at N2, and this electron is located at N1, meaning that this is the highest energy level orbital, and this orbital is the farthest from the nucleus. So when we are about to remove electron from transition metal atom, we need to remove from the outermost orbital or valence shell. For example, the electrons from 4s orbital in ferrum 26 will be removed first before the electrons in the 3d orbitals. Let's say we are going to have this electronic configuration of ferrum 2+ ion. So in order to form this ionic electronic configuration for transition metal, we have to remove as much as 2 electrons from the valence shell. So removing these 2 electrons, we will get 3d6. And in order to form ferrum 3+, meaning that you have to remove as much as 3 electrons. But here, we only have 2 electrons at the valence shell. So the other 1 electron will be removed from this 3d orbital. So hence, you will get this electronic configuration for ferrum 2+, ferrum 3+. So ferrum 2+, we remove 2 electrons from the 4s orbital. For ferrum 3+, we remove 2 electrons from the 4s and 1 electron from the 3d orbitals. To understand better, let us write this orbital diagram so that you can see on how we can remove the 2 electrons from the neutral atom to form the ferrum 2+ ion. In order to form ferrum 2+ ion, 2 electrons will be removed from the valence shell, that is 4s. Now, let's do for ferrum 3+ ion. Let's remove 3 electrons from the neutral atom to form ferrum 3+ ion. In the case of ferrum 3+, 3 electrons must be removed from this neutral atom. The 2 electrons will be removed from the 4s orbital, and the other one is from 3d orbital. In this case, by removing 1 electron from 3d orbital from the paired configuration, daripada konfigurasi yang berpasangan, later we will form 5 single electrons in parallel spin, which is more stable. You cannot remove this single electron from this position because removing this electron later will form unstable configuration in this ion.
With you, I can be sad with you. Just take my hand and fly up through the dreams where the skies are so clear.
Thank you for watching, everyone. I hope this video could help to enhance your understanding in chemistry. Have fun in your learning, and remember, chemistry is easy and fun.
I love the way that you